Howdy, everybody. Welcome to the 2024-2025 Lunabotics SRR. The goal of this is to present a understanding of the rules and the requirements that gives to us on our design, and then make that known to everyone in the team. So, here's the itinerary for today. We have a quick project timeline, and then some general requirements on the system. We'll talk a little bit about the competition, and then we'll talk about our deliverables, and then get to the sub-team specifics. Sorry. All right, so here's the overall project timeline for Lunabotics. The guidebook came out in September. We have our project management plan that we need to finish by the 3rd. By the 3rd. Our tentative plan for the PDR is going to be the 19th, so mark your calendars for that. So we're going to go over our design, and we'll hopefully have a large amount of industry in here. So yeah, critical design reviews slated for the 20th of November. STEM engagement report, this is a NASA deadline, is due January 15th. The systems engineering paper will be April 9th. And then systems verification review will be March 31st tentatively. And then proof of life video will be due April 21st. And then competition will be the week after finals. That's going to be May 15th through 22nd, 2025. All right, so we got a review of our Gantt chart here. I know it's hard to see some of the dates, so if you need to look at that more closely, please email me and I will send you the it in a more viewable manner. Yeah, so some general requirements for our design is the robot must be 1.5 meters by 0.75 meters by 0.75 meters. At most, it can be 80 kilograms. We have to have an e-stop. That must turn off all voltage above 5 volts. And then, yeah, the goal of it obviously is to excavate and move regolith and then build with it. For some design restrictions, no sensors can use the walls or arena. It's a limit for navigation. And then for safety, we need PPE in the test arena. NASA will provide that. But if we get our test pit, we will also need to make sure we have the safety requirements for our own test pit. Yeah, so brief bit about the competition. Here's the arena for the NASA. This is the NASA arena, so that is if we get in the top 10 from the preliminaries, we'll go to this. So the idea of this competition is the robot is going to start in the starting zone over there. It must go through the obstacle zone without hitting anything, or else we get a point deduction. It can then excavate in the excavation zone, take that material and drop it off in the burn area of the construction zone. We are not allowed to take regolith out of the build area to use for that. We must only take from the excavation zone, though they did add bulldozing is allowed, so as long as we're not trying to gain material from the construction zone, material from the construction zone can be used. There will only be obstacles in the obstacle and excavation zones. The obstacles in the excavation zone are allowed to be moved and will actually count towards regolith volume if we move it into the burn building zone. Anything on this, Tillman? All right. So there are a few main deliverables that we have got to do as a team. First is the systems requirement review. And then we'll have our project management report. That is what we submit to NASA to say, hey, we want to be part of this competition. Here's our plan for doing this competition. That, as I said, will be due the 3rd of October. We will have our preliminary design review, review of early stage designs before we begin development. And then critical design review, a more in-depth, last-minute, let's check things before we make expensive mistakes. We have our STEM engagement report. That's going to be us talking about all the outreach that we did. Yeah. And then, bless you. And then, yeah, we will also have at the end a systems engineering paper, which will be a in-depth review of our system and how we put everything together. So team goals for this year. We are looking to follow systems engineering practices to follow NASA's model for real projects. Again, this is a systems engineering competition more than anything else. And so we want to make that a focus of our team. We want to design with a path to flight in mind. That meaning everything that we use has to have an analog for the moon. We don't have to use space grade parts, but everything we use has to have an analog there. So we can't use ultrasonic sensors because there's no air to use then on the move, stuff like that. We want to make the design as simple and effective. We have a big focus on the autonomy this year, and it makes it a lot easier to make an autonomous robot if we have less things to worry about. Again, like I said, we have to do engagement, so we want to focus on STEM engagement, especially in the middle and high school age range, but all throughout the local Cleveland area. Again, we're all here to be better engineers, so we want to develop and share skills useful in professional engineering world. It's all about becoming better engineers and better people, right? And then a little reflection from last year, we want to minimize single point failures. Both of our runs were lost due to single point failure components failing. So we want to minimize those as much as possible so that we can hopefully do better this year. So quickly to present on the mechanical sub-team is our mechanical lead, Jared.
Hey guys. So pretty simple. We have a few goals this year. We're trying to take 10 kilos off of the weight. Last year we had 79.5 kilograms out of 80, so we were right up against the maximum weight. So if we can get down to 70 or less than 70, that'll be really nice because it's now weighted against the it's scored based on the weight of the robot now. So having a heavier robot is actively detrimental. We're trying to reduce the mechanical complexity of the systems. That's last year's design, so you can see it was not a simple system. So if we can fix that and reduce the amount of stuff that we push out of the other sub-teams and make it mechanically simpler, we're going to have less failure points and it's going to be easier for them. We're hoping to increase the total torque output by the motors. Last year we had about 240 meters of torque, 120 per side. This year we're trying to get up to 300 plus Newton meters of torque. That'll let us look into different types of excavation systems, so like bulldozers or front loaders or stuff where you actually have to dig in, and with less torque you're going to get stuck. But if we have 300 plus Newton meters, it shouldn't be a problem. And then just increase the reliability of subsystems. Last year we had a lot of problems getting the bed centered when it would come back down because we have a whole bunch of wear on the rear hinge. If we can fix stuff like that this year, so that we don't have to constantly repair it as we go along, that would be great.
All right, so for the electrical sub-team, just some changes from last year, some goals that we have based off of last year. We need a more controlled and reliable motor control system, I guess. There's a lot of finicky things that happen with our last motors. It's kind of weird to change the direction, change the speed of the motor, so we're going to fix that. I'll explain that on the next slide. We want to, with our new motor system, we'd rather, instead of trying to track the motor's revolution through the way that it spins, we want to just let the motor spin and then use some sort of external source to monitor how many revolutions the motor has spun. A big issue was we had, when you have like a battery that it depletes capacity of voltage and drops, and so we had some issues with our voltage dropping, and then we had grounding issues and brownout issues, and we had a power cleaner, I guess if you want to call it that, that's supposed to output a constant voltage, but it ended up being the wrong component. So we just want to make sure that it's a little bit more solid this year so that we understand what's happening electrically with the power distribution, especially with cable and the cable management and labeling. We need to be a lot better this year with being able to tell what's happening just by looking at it. We had a cobweb of wires last year, so that's going to be almost top priority for this year. Another thing is we had sort of like a makeshift box last time to store all of our electronic components, and it was more designed around our mechanical design initially. So we want to try to keep that in mind. Maybe ideally we'd have a sealed box, so instead of designing a box around our existing design, maybe we can incorporate it more into the official design. And then because we're going to be adding sensors and there's a lot of both signal and power, we'll support the computer sub-team with powering and routing signals. So like I said, upgrading the motors, we want to look at some brushless AC motors. Technically they're DC motors, but they're 3 phases. They'll draw less power. We can use brushless DC motors that have a gearbox on them already built, so that will give us more torque, less power consumption. And then, of course, we have all that going into our gearbox that's already mounted on the chassis, so we should get a higher torque output overall. Like I said, we want to have like some sort of encoder on maybe the motor shaft, so as the motor spins, basically you have like a magnet with a sensor that detects how many times the magnet passes it, so you can determine how many revolutions the motor has made, and thus how you can do reverse kinematics to figure out how far the robot is supposed to move. And then, like I said, we need a new power filter this year for constant output voltage from our main battery. And then we got a new power monitor that was donated to us from one of the teams during the competition, so we want to properly include that into our power diagram. And then, yeah, power management and distribution, we just want to make sure we have proper harnessing. Probably, it would be ideal to use more connectors so we can quickly disconnect and add components, swap components in the event of a failure. And then, of course, last year we sort of did this, but we'd like to do it a little bit more officially, where we have a high voltage battery that powers all the high voltage components, the low voltage battery that powers like our computer. We use like a portable USB power bank, so ideally this year we would use something a little bit more robust.
All right, so I want to talk briefly about some of the computer goals for this year. So the main goal of our subsystem is, again, to control everything. This is done through motor control, localization, path planning, and error detection. I got a list here of our primary concerns that I'm going to go. The robot has to be able to detect where it is in the arena. Not only are there specific functions that we can only do in certain parts of the arena, but if we dump regolith into the wrong area, we get no points for it. So we have to know where we are in the arena at all times. As I stated earlier, everything has to be usable on the moon. That's especially important on the sensors. GPS doesn't work, magnet-based compasses don't work, and anything using the air, like ultrasonic sensors, do not work as well. Specifically, walls cannot be used for localization. There's not going to be walls in the lunar environment, and so we are not allowed to use them. We are allowed to avoid them as an obstacle. They don't want us running into the walls, but we cannot use them for any sort of localization. And then the robot also has to work for both maps. The arena for UCF and for NASA Kennedy are different, ever so slightly. And we have to be able to work in both of those environments, make sure we're in the right burn box, make sure we're excavating the right zones, and not running into any obstacles. So, some secondary concerns that are not as important, but still should be think about. We do want to minimize power usage. Computer's not a large area of the power usage for the robot, but we still should keep that in mind when we're picking a controller. We do need to minimize data usage, especially if we are controlling manually and not autonomously. We need to send controls easily, and we need to make sure that any image we're sending back, so we can see what the robot is as compressed as possible, because we lose points for all the data that we use. It's got to react to changes made by itself. I've seen robots get stuck in their own holes that they dug. We don't want to have that problem, and so it has to be able to understand, we don't want to dig a trench and then fall in our own trench. If possible, I would like to avoid using situational cameras. Those are the cameras mounted on the top of the arena. They cost an additional 200 points for every one that we use, so if we can avoid using them, that's 200 points we save. And then last year we had a failure due to hardware timeout. We sealed the box too early, and we waited longer than we thought we did. Our hardware timed out, we couldn't connect to it. So we need to either plan on putting a reset button somewhere where the setup team can hit it, or we need to just pick hardware that does not have time-based timeouts. So that is it for the presentation. Is there any questions? Cool. Well, thank you all for showing up. I think we're going to split into sub-teams so we can kind of discuss the stuff reviewed in the SRR.